Okay. Never mind. Okay. We don't forget that we do have a test next week. Monday is going to be for the review. Wednesday will be the test. Just keep that in mind. The study guide is on LMS. You are welcome to go look at that. All right. So we're going to start into the last little bit of chapter 7. And we're going to be talking more about ionic compounds, and then we'll get to a little bit of metals as well. So we started talking a little bit about ionic compounds last time. And remember, we have positive and negative. And these opposite charges interacting with each other, that's what hold these atoms together. You have the positive and the negative holding it together, just like magnets. And once again, if we have sodium, which is a +1, chlorine, which is a -1, we build these big crystals. But when we talk about them, we want to talk about it in the simplest ratio possible. And this, as you can see, is a 1-to-1 ratio, right? For every sodium, we get 1 chlorine. That's why when we write it, it's just like that. But if we replace the sodium with magnesium, things change just a little bit. Because our formula unit, it has to have a total charge of 0. So if we put magnesium in there, we look at the periodic table and we say, oh, it's in group 2. So if it's in group 2, is it likely to gain or lose electrons? No. More likely to lose, right? Because it only needs to lose 2 electrons and then it goes to the next lowest shell. If we're going to gain, we'd have to put 6 electrons in to get to 8. Okay? But it's going to lose 2 electrons. Sodium is only going to lose 1. Throwing everything everywhere. Sodium is only going to lose 1, but magnesium is going to lose 2. So magnesium has a +2. Okay? Has a +2 charge. So if we were to stick a chlorine, which has a -1, the total charge on this is still going to be +1. How can we solve that? Well, it's actually pretty easy. We just have 2 chlorines. So the formula unit is MgCl2, because that gives us a net charge of 0. So when you're dealing with ionic compounds, that is something to remember. The formula unit needs to be electrically neutral. It needs to be electrically neutral. Does that make sense? Yes, no, sort of, kind of, not really at all. So what we next want to establish is what to call this. This has a specific name. That name happens to be magnesium chloride. So how do we know that? That's what we're going to talk about today. By the end of today, you're going to know how to name ionic compounds. I'm going to be able to give you an ionic compound, and you're going to be able to tell me what the name is. Isn't that fun? Okay. So we name it based off of the formula unit, where we have the lowest possible ratio of how they come together. There are, so if you look at page 218 and 219, there's two tables there that have a bunch of common ions and what their charge is going to be. In table 7, you can see pretty straightforward, got a list of them, what their charge is. Table 8 is a little bit less helpful, I guess. I don't know if I want to use the word helpful, but it's a little less clear. We'll say that. So if you look at group 4, it's got titanium, but it says titanium can be 2+ or 3+. That happens. Remember, we mentioned that the transition metals are a little bit, they do different things. A lot of the ions that you see in table 8 have two possible charges. So what does that mean when you're doing formula units? Well, let's talk about something like iron oxide. Okay. Now, oxygen, pretty straightforward. We find that in 7, okay? And it's going to be 2-. Iron, however, is one of these transition metals. And there are two possible charges. We look, group 8, it's right there. It can either be 2+ or 3+. So that means we have two possible formula units. It is possible to have one of each, or we can have that. You see how the charges are 0 on both options? This one, 2+, 2-, pretty simple. This one, 3+ and 2-. So we have 2 of the 3+, which is a total of 6+, 3 of the 2-, which is a total of 6-. So one thing that you may not have noticed we always write the cation first. Okay? We always write the positive ion first. If you were to go to a chemist and write that, they would know what you were talking about, but it just looks wrong. Okay? Because we, as chemists, decided we're going to write the cation first. Okay? So we write it like that. Not like that. And that's what we decided, and that's how the naming rules are going to work as well. Okay? But before we really get into the rules themselves, I do want to point out sometimes we can have what's called a polyatomic ion. So what does poly mean? What is poly? Anyone know?
Like unnatural.
No. It means many. So polyatomic means it has many atoms. So if you look at page 221, we have these groups of atoms that are stuck together, but they are actually bonded together with a type of bond that we haven't talked about yet called covalent. We'll get to that after the test. But they're stuck together, but that group, the whole group, ends up having a charge. And so it can act just like one of these ions. We get this group of atoms together, but because it has a charge on it, it acts like if it were just one atom. I will not expect you to memorize those. Okay. Anytime you are doing homework or test or whatever, if you're dealing with a polyatomic ion, I will give you that information, what it's called. Now, a lot of those I have memorized, mostly just from using them quite a bit. But I've never sat down and decided I was going to memorize them, and I don't expect you to either. So just know that they work just like a single ion. So let's actually look at this example, finding the formula of a polyatomic ionic compound. So we're on page 222 right now. And it says, a compound formed by calcium ions and phosphate ions is often used in fertilizers. Write the compound's formula. Okay, so calcium ions, the first thing. We look, we find calcium right there, okay? Number 20. It's in group 2. So what kind of charge should we expect on calcium? Positive, yes. Positive what? Positive 2. Okay. And then we look at the table on page 221 and find phosphate. It is on the right-hand column, second from the bottom. And it's PO4 3 minus. Okay. So we have our two ions. Remember, this is going to work just like if this were a single atom. So we need to get the ratio that's going to give a 0 charge. Well, we're going to need 3 of these and 2 of those. Does everyone see why? Yeah. So this is going to end up being 6 positive and 6 negative, so they cancel each other out. So how do we write that? Well, we put our calcium with a little 3 as a subscript. For the polyatomic ions, we put them in parentheses. What those parentheses mean is that acts as a unit. Okay, this acts as 1 unit, but we have 2 of those units. Okay. So that's how we would write it. If you don't put the parentheses, then it looks weird because you have a phosphorus and then it looks like you have 42 oxygens, which is just weird. That wouldn't actually work. So use the parentheses. I mean, technically, could you write that? Once again, everything it's there. It's kind of like writing the chlorine first. We could figure out what you're trying to say, but that is the correct way and the way that is honestly easier to do. So yeah, we treat that just like if it were single. All right, now let's talk about names. We have a set of 5 rules that are listed on page 223. They're pretty straightforward. Okay. Rule number 1, name the cation followed by the anion. So we've already really established that we write the cation first. Right? So that one we already really knew. And all that's saying is we're going to have it first in the name too. So you write it first in the formula, you say it first in the name. Okay, number 2. For monatomic cations, all you do is use the element name. Okay? So what element is that?
Calcium.
Calcium. So the name, we just say calcium. Okay? Rule 3 is for monatomic anions, so we'll come back and look at that one. We're actually going to go all the way to rule 5. When a compound contains a polyatomic ion, just use the name of the polyatomic ion. So it's calcium phosphate. All right? It's not overly complicated. Calcium phosphate. Have the element name and the polyatomic ion name. And we got it. Calcium phosphate. Let's go back and look at the other ones that are monatomic. So rule number 3 says for monatomic anions, use the root of the element name plus the suffix "ide," I-D-E. So it gives us this example. So we have CSBr. So rule 1, CS is cesium. And then we have bromine. So we use the root of the element, which for bromine, we take off the INE. Okay? So that leaves Rome.
This is short name, right?
Yeah, we get rid of the last chunk. And then we replace the INE with IDE. Okay. So this one is cesium bromide. Okay. So let's do some other practices, because that's how you're really going to get it, is just to sit down and practice with it. So let's look at on page 223. So we've got several ones that we'll just go through here. So NaBr. Who can give me a name for that?
Sodium bromide.
Sodium bromide. Good. Sodium bromide. Okay. Next one, CaCl2. Calcium chloride, exactly. Okay. Ooh. We have a polyatomic ion in there.
Oh, potassium oxygen.
Okay. So where's the polyatomic ion in here? Let's go back and look at page 221 and see if we can find hydroxide. So right here, that's hydroxide. Okay. So knowing that, what does that name become? Potassium hydroxide. Remember, when you have a polyatomic ion, you just use the name. Those ones are actually super easy because I don't expect you to memorize them. So you look it up and there's your name. Okay, let's look at what we have here. Copper nitrate. Okay, so Cu is copper. NO3 represents the nitrate ion, the copper nitrate. What about that one?
Silver.
Silver something. So what we need to find is CrO4 on our polyatomic ion. Chromate. It's silver chromate. So it takes a little bit of practice to get it down, but it sounds like you guys are starting to get it. Take the cation, which is just either just the element, or we can have a polyatomic cation. Okay. So you take that, whatever name it is, figure out the anion. If it's a polyatomic, just whatever name it is. If it's not, it's monatomic, then use the root, take off the last N, the last part of the name, and replace it with IDE. So. Okay. So we're probably going to finish up a little bit early because we only have one section left, which is metallic bonds. I doubt any of you will be too upset about that. So, metallic bonds and the properties of metals. Now, these bonds are a little bit weird because they're not true bonds, just like ionic bonds aren't really true. The words, the terminology that your book uses is called a sea of electrons. And basically what it's saying is, with metals, you have a whole bunch of positive atomic nuclei. Okay, we got the protons, makes them positive. And they're all there, but the electrons don't necessarily stay on the same nucleus all the time. Okay? Which means that the outer levels of these electrons are actually free to move about between these different nuclei. So if you have, an atom here, an atom here, you've got a whole bunch of electrons. Another one here, I guess we'll do that. This one right here, it can move over here. Okay? It does that. They all just kind of move around without being tied to a specific nucleus like we find in the other things. So a metallic bond is simply saying, well, there's this sum total of interactions. Okay. So this has some effect on their properties. Okay. Once again, anytime we talk about properties, we have to make sure we understand that, each element has its own properties. You can't say all of these have this particular property. And even if they all have that property, they all have it in different amounts. Anyway, but let's just kind of talk about it. First thing it talks about is melting and boiling points. The melting and boiling points for metals has a huge gap. Okay? There's a really wide range. We do have mercury right here, which is a liquid at room temperature. Mercury is a metal that is a liquid at room temperature. Its melting point is, well, this is listed in Kelvin. It's 234 Kelvin, okay? Which is below 0 Celsius. So it has a very low melting point. And you can actually get mercury to boil at 630 Kelvin, which is about 350-ish Celsius. So not super hot. But then we come over and look at tungsten over here. That doesn't melt until well into 3,000 degrees. And yes, you can get tungsten to boil, but you have to get it up to 6,000 degrees. So, 6,000 degrees, by the way, is about the temperature of the core of the Earth. So it takes a whole lot to get tungsten to boil. Anyway, so it's hard to, really say that there's a specific pattern for melting and boiling points for metals, because it's a really wide space. Most of them, however, have not like super high melting points, but relatively high. Typically for metals, you do have to put in a fair amount of heat to melt. Okay, the next one, you may not have ever heard these words before, even those of you who grew up speaking English. Malleability, ductility, and durability. Now maybe durability you've heard, but Malleability and ductility, those are kind of weird words. But really what it means, so malleable means you can have a chunk of a metal and you can hammer it flat into a sheet. That's what malleable means. Okay. Ductility means you can have a chunk of metal and you can squeeze it into a wire. Okay. So malleability, you can hammer it into a sheet. Ductility, you can make it a wire. Okay. Metals tend to have those properties, largely because of this and how the atoms can rearrange without it being too much trouble. And then, of course, durability. Metals are generally really durable. Now, some of them undergo chemical reactions, which make them less durable. But if you just have a chunk of metal that's not exposed to anything that will react with it, it is a pretty durable thing. So it's not going to really fall apart. Thermal and electrical conductivity. Metals conduct heat pretty darn well. Now, the chairs that you're sitting in, they have metal legs on the bottom. So if you were to reach down and touch the leg of the chair, it'll feel cold, right? Is the metal actually cold? No. Metal is the same temperature as the room. So why does it feel cold? Okay. The metal is conducting the heat out of your hand very efficiently. And so heat from your hand is going into the metal, which makes it feel cold. But that metal is honestly the same temperature as the room. So that's what we mean by thermal conductivity. Electrical conductivity, that's pretty straightforward. It conducts electricity. We use metal to conduct electricity. Different metals will conduct electricity better than others, but most of them will at least do something. Hardness and strength, once again, huge gap between the ends of that, so we're not really going to discuss it too much. But I do want to mention alloys. So when we use the word alloy, what it means is we've taken two metals and mixed them together into a homogeneous mixture. So if we take, honestly, really any two metals, mix them together, we get a blend of properties. Now, some alloys have some really desirable properties. For example, steel. Okay, now, steel is a very strong alloy. And what we've done is we've taken iron and we've mixed it with carbon. Okay. Now, carbon isn't technically a metal. Most alloys have two or more metals, but we can throw non-metals in there sometimes. There is, on page 228, a list of commercial alloys. These are just common ones. You've probably heard of some of them. Brass, you've probably heard of. And it tells you brass is a mixture of copper and zinc in anywhere in those proportions. So as much as 90% copper or as little as 67% copper. And then the rest zinc, depending on how much copper. Bronze is almost identical to brass, except it's added tin in as well. Cast iron, gold, pewter, stainless steel, things like that. So when you hear alloy, just remember we've got a metal mixed with one other thing, usually another metal, but sometimes, like the case of steel, we have carbon in there instead. So now the book goes into substitutional alloys and interstitial alloys. I don't care anything about that, so don't worry about that. So. And that actually is the end of the chapter. So we do have almost 25 minutes left. So I do have a short homework assignment for you, but you could probably just about get it done in 25 minutes. So I'll put it on the board and you can. I did have a homework assignment for you. I wrote it down somewhere. Wherever I wrote it, it disappeared. So let me rewrite it so I can give it to you real quick. Sorry.
It all looks so right.
Okay. So yeah, you've got about 20 minutes. Go ahead and get started on that.